All right, let's go over these free response for our Unit 6. Discrete random variables and sampling distribution. So here we have this problem where we are told, first of all, that the population of days, absences on the days, is approximately normally distributed. It's averaging 120 students with a standard deviation of 10.5. Okay, so imagine taking a value for all the school days. And there would be, on average, 120 students absent. But if more than 140 are absent on the day that they pick, then they're going to lose funding. So the first question is, what probability that they will lose funding? So this is asking about one day, and we can do one day. We can do z-scores and normal model math about one day because we are told it's approximately normally distributed. So that's why then I put then the x minus the mean over that population standard deviation. There's the z-score, and then I norm CDF. So if they are really averaging 120, okay, with that standard deviation, then there's just about a 2.87% chance that they would lose state funding because they would just happen to pick one of those days that's above 140. All right. So you had to use this correct. So there's how you basically you had to do that to get credit. Okay. Now, look, you had to indicate the use of the normal distribution clearly and identify the correct parameters. So I'm going to mention to you, this is your ticket for this one, saying z equals. If you leave off z equals, then you now have not identified this as the normal model. Okay, that's a big deal. And I taught you that earlier in the year. So that's critical that you put that z equals to get credit for this first part. All right, next, part B. So now they are going to take 3 days chosen at random. So that's going to be an average, an X bar of 3 days. This is now making a sampling distribution where we have we don't have individuals anymore. We don't have individual days that average at 120, okay? But we have now averages. See how it's going to be taller and skinnier? And these are X bars, average of 3 days, average of 3, average of 3. So what happens is, if this is 140 right here, this was 2.87%. This is going to be very little, if any. So the reason that is because we have a smaller standard deviation, and that had to be shown here. Look, the standard deviation is that 10.5 divided by the square root of that sample size 3. So then you redo the math. And see, now I say z equals 140 minus 120 over that 6.06. So look at that. The high school is now much less likely. So to get credit, you had to say it was less likely to lose funding for the average of 3 days, because it is less likely for that average of 3 days to be greater than 140. And you had to say why. Justify your choice. Because the variability of the samples is going to make it more closely clustered around the center. So then that makes less samples out there on the side. Now let's look at full credit, how they actually did this. So that's hard to read. Clearly, I don't even, indicates that the variability is smaller. Okay, so to get full credit, clearly indicates the distribution of the sample means. Aha. Indicates the distribution of the X bars now of samples of size 3. Indicates that the variability is smaller. Indicates that the distribution is still centered at 120. So see, by doing this here, I cover all these 3 components. All right. And then has that, and did all of that up there, and has the correct calculation, and states that it is now less likely to find an average of those above 140. Lots of stuff there. Now, this one was just a situation where we said, what's the probability that none of the 3 days chosen is a Tuesday? So, of the week, is it Tuesday, Wednesday, or Thursday? So 3/5, I forgot to put that in there. So 3/5 of the week is a Tuesday, Wednesday, Thursday. So 2/5 of the week is 40%. So Monday or Friday, and this one's a Monday or Friday. Oh, there it went. Looks like that right there got moved. And this is a Monday or Friday. And so that's then why it's 0.064. All right, next. Here we have a 2010 problem where they asked you to describe describe the sampling distribution for samples of 40 rock and roll songs. So the sample size is 40. So what that means is that, yes, the population is centered at 3.9 with a standard deviation of 1.1. But again, okay, so let me draw this picture so you understand what's happening. So this is all songs, all individual songs ever, all songs ever, all songs ever are centered at 3.9 with that standard deviation of 1.1. But if we take samples of size 40, then we have this. We now have an average of 40 songs, 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 and so on. And this standard deviation for these samples is smaller. It's 1.1 divided by the square root of 40, which is now 0.17. That's the big deal to understand what's going on with this problem. All right, so that means that when we describe the sampling distribution with our SOCs, we are saying that it is approximately normally distributed, unimodal symmetric, and you can say it's approximately normal because you know that 40 is a sample size that's large enough according to central limit theorem because it's greater than or equal to 30. All right, outliers isn't really something they looked for because they didn't give you specific things. If you wanted to, you could compute where the fences are and say anything above the upper fence or below this lower fence, okay, would be outliers. And now the center of this the center of the sampling distribution is still centered at 3.9. See, our songs will still be centered, the average at 3.9, but the standard deviation is less. The standard deviation of the sampling distribution is 1.1 divided by the square root of 40. So now that we have identified these things here, we now do the math here. So they say, what's the probability that these 40 songs will have an average of 4 minutes or more? That's what they're asking. So see, look, here's my z-score. 4 minutes minus the mean over the standard deviation. And there's that z-score, and then I norm CDF'd that, and that's how I got 47.65% chance. So there is that. Now, you could have done everything in terms of minutes. And if you had done this, and this was acceptable, if you had done that, then you multiplied everything by 40. So see, that became 160. 3.9 times 40 is that. And your 0.17 times 40 is that. Okay, so that works out that way. Same standard deviation, or same z-score and standard deviation. So you get essentially correct if you have the correct calculation. If not, then you don't. You get, I'll have to look at what gives you partial credit on that. All right, and that's all that there was on that problem. So now, here's the 2008. This was version B, but I really liked this problem, and they haven't had one like this on a regular mainstream form. This was just the only one that showed up on this B, but man, this is a good one. This really talks about how the graphical representation of the data looks when it is biased. So I really liked this. So here, see, the true value of the population parameter is centered at 75. So it needs to be centered here at 75. And therefore, you can see statistic B is biased because it is not centered at 75. Why is it biased? I don't know. Maybe they had response bias, all those different things that could cause bias that we talk about: voluntary response bias from lack of privacy. Um, we have had another, lots of different reasons that your parameter could be estimating it too high. They were volunteers. These were adults who liked physical fitness, so they were overestimating the something or other, and so on. So statistics A, C, and D are unbiased estimators because they are the ones centered at 75. And you had to state both of those, which ones and why, to get full credit there. B, which of the statistics A, B, or B would be better estimator for the population parameter? Well, obviously A, because it is not biased. B is the one that is biased. So you had to state that B is not centered, it is biased, it's not centered at 75. And then what about this one? Which one's better, C or D? Well, hopefully look at D. It's high variability. C is much better because it's less varied. Now, it's not as good as A. C is not as good as A, but it is better than D. So in order of the best representation of the population, I would say A is the best, C is the next best, D is the third, and B is the worst because it's not even centered in the correct place. All right, and the last free response. Here we go. Again, this is about the sampling distributions with a sample of size 15 versus a sample of size 50. So we have this situation here where they even on the actual AP free response grading guidelines, let's see, when was this? This was 2007, so quite a bit. They had a picture as what they kind of expected you as a very good way to demonstrate that, see, look, samples of size 15 centered at 8 and samples of size 50 centered at 8. And then they both asked about being greater than 10. So this is samples of size, this is a sample of 15 fish and their average length. This is a sample of 50 fish and their average length. So each one of these X bars is an average of fish and their lengths, whether it is 15 fish up here or 50 fish down here. All right, so to get credit here, the question was which is more likely. I did bad. I kind of did the opposite. I didn't say which one's more likely. I said which one was less likely. I think I would have still gotten credit because it's one or the other. So, which would they be more likely to find? And this area being great, a sample mean greater than 10 when the samples are size 15, or the sample mean greater than 10 inches when the sample sizes are 50. So here's what you had to do to get credit. It's essentially correct if the student says the sample of 15 fish is more likely to have a mean length greater than 10 and justifies it based on the variability of the sampling distribution. Big deal right there. So you had to say how this, let's see. Did I do that? Yeah, look. Samples of size 15 have more variability than samples of 50. That's what you should note because changing that in changes the variability, the standard deviation. Okay? That's the key you're supposed to get. So this has more variability. And because of that, there is a higher proportion above 10 inches with this sample mean than this one down here's sample mean. Now, I stated it backwards. I said it's more difficult to be down here instead of saying it's more likely to be up there. But it's the same idea. Next. Now, Supposed standard deviation for random samples of size 50 is 0.3. So they are saying the standard deviation for these X bars is 0.3. So the standard deviation for these X bars is 0.3. Okay? So then you just do this here. X minus the mean over the standard deviation. Now look here. So there is a 4.75% chance that the random sample of 50 fish will have an average less than 7.5 inches. So look here at the grading guidelines. This is why you have to, again, say Z equals and put everything in order. That has to be there because to get credit, the components are clearly identified and labeled. If you do that right there, you have covered your hiney on that components being identified and labeled because that's a standardized formula. All right, and finally, this one would catch so many people because I'm afraid you might not actually say the words central limit theorem, and you would have gotten marked down from an E to a P. So let's take a look at this. Suppose the distribution of the fish links of the population was non-normal. Okay, so here's what that's saying. The population of the fish links non-normal. I don't know what it is, but it's not normal. Okay. Then the question is, let's see. Would it still be appropriate to use the normal distribution to compute the probability in part B? Yeah, the one where the sample size was 50. Well, what do you have to say about that? Okay, here's what most people would be inclined to say. Yes, because the sample size is greater than or equal to 30. All right, and that is partial credit. To get full credit, you had to say yes, because the central limit theorem says that if the sample size is greater than or equal to 30, then the sampling distribution is approximately normal. See, to get full credit, the central limit theorem and refers to the large sample size. Mentioning sample size without central limit theorem is partial credit. Now, remember what central limit theorem says. Central limit theorem says if n is large enough, then it does not matter the shape of the population. The sampling distribution of sample means is going to be approximately normally distributed. If n is large enough, then it doesn't matter the shape of the population. The sampling distribution's about normal. Okay, central limit theorem is about the shape of the sampling distribution and the parent population. All right, that is the conclusion of the free responses in this review section. So I hope those did you well and that you caught lots of little things to make yourself getting full credit on the actual AP exam.